Good morning, dear students. Today we will discuss electric dipole. Electric dipole, and we will derive the expression for electric field intensity at its equatorial point and axial point. So, first of all, what is electric dipole? Electric dipole is an arrangement of two charges which are opposite in polarity and equal in magnitude, separated by a distance L. So, an electric dipole is a combination of two charges, minus q and plus q, and the distance between the two charges is L. And this distance, this dipole length, this distance also called the dipole length, must remain fixed, then this arrangement is called an electric dipole. Electric dipole. So, the quantity we define for this physical quantity we define for this electric dipole is known as electric dipole moment, which is a vector quantity which is given by the magnitude of one of the charges and the length of the dipole. The direction is conventional, is taken from minus q to plus q. If I take this like my coordinate system, suppose this is my unit vector I, then the direction will be given by this unit vector I. So this is the electric dipole moment. The quantity electric dipole moment gives us the strength of this electric dipole. Now our job is to calculate to know what is electric field intensity due to this dipole. For that, we already know that electric field due to a point charge. If I have a point charge Q here and I want to know the electric field intensity at point P, which is at a distance x from this point charge, then I already know that this electric field intensity at point P will be given by E is equal to 1 over 4 pi epsilon naught Q over this distance square. This gives me the electric field intensity, and depending on for determining the electric field intensity, we place a unit positive test charge here. This already we know, and then the direction of the electric field intensity is away from this point P. This is the basics we need to determine the electric field intensity due to an electric dipole. Suppose this is an electric dipole, minus q plus q charge, and conventionally we take this separation distance as 2a. The L distance or the length of the dipole is taken as 2a, actually for solving the problems. So at point P, on the axial line of this dipole, that is along the dipole, I want to know the electric field intensity due to this charge combination minus q plus q. Suppose this distance already is 2a. Suppose this is the center of the dipole, and from the center this point P is at a distance r, and if this point is at a distance r from center O, then this point charge minus q is at a distance of r plus a from point P, and this charge plus q is at a distance of r minus a from the point of calculation or point of observation where we want to calculate the electric field intensity due to this charge combination. Now it is easy. Now we will individually calculate and see what is the electric field intensity due to minus q and then due to plus q, and then add them to get the net electric field intensity. So if due to the plus q charge, I will write E plus q. That means the electric field intensity due to plus q is equal to 1 over 4 pi epsilon naught q over the distance square, and the distance is r minus a whole square, and its direction will be away from the point P because it is a positive charge. So the force of the Coulomb's force at point P will be a repulsive force away from the point P. So the electric field intensity will also have the same direction, that is away from point P. Similarly, I can write the expression for electric field intensity at point P due to minus q charge. That is 1 over 4 pi epsilon naught q over r plus a whole square. Now this will be attractive. E minus q will be directed inwards, whereas E plus q will be away. Now we know that the electric field intensity at point P will be greater by plus q because the distance is smaller, and due to minus q the electric field intensity will be lesser, will not be so much. So to get the net electric field intensity, I will subtract E net on axial line will be E plus q minus E minus q. This will be the net electric field intensity at point P. So I will take 1 over 4 pi epsilon naught, or I can take q over 4 pi epsilon naught as common, and I'm left with 1 over r minus a whole square minus 1 over r plus a whole square. Why I have subtracted here? Because the directions are opposite. The angle between these two is 180 degree. So I will get the net electric field as on the axial line q over 4 pi epsilon naught. It will be r square plus a square plus 2ra, and it will be here r square minus a square plus 2ra, just a cross product, and in the denominator I have r square minus a square whole square, because I have used the identity a minus b into a plus b, that is a square minus b square whole square. So this gets cancelled here, r square, a square, and I'm left with here the net electric field on the axial line of electric dipole is q over 4 pi epsilon naught 4 r a over r square minus a square whole square. This is the net electric field intensity for this arrangement of two charges minus q plus q that forms an electric dipole at point P on the axial line. I can express it in terms of dipole moment. So I know that the dipole moment is P is equal to A into R. So I can write E net axial is equal to Q into 2A. This quantity gives me the electric dipole moment, and then I'm left with 2r over 4 pi epsilon naught r square minus a square whole square. So this gives me q into 2 is p, electrodipole moment, and this is the expression for the electrodipole moment. Expression for electrodipole moment on the axial line. The direction of this electric field intensity will be in the vector form. It will be, if I write it as E net on the axial line, it will be same as the direction of dipole moment, that is from minus q to plus q. 4 pi epsilon naught r square minus a square whole square. Now, for a special case, when the electrodipole is very short or very small electrodipole, that is this separation distance is very small and this point P is far away from. Generally, this distance from, that is the dipole length, is of the order of angstrom or nanometer or even micrometer. So, but if this point of observation is at some millimeter or some centimeter, then this r becomes far greater than a. So in that case, I can safely write this r square minus a square equal to r square, because r is far greater than a. So for a short dipole, I can write E net axial equal to 2p over, I can replace this by r square, then this is square, and then this becomes r power 4. One of the r gets cancelled, so I am left with 4 pi epsilon naught r cube. This gives me the electric field intensity due to a short dipole on this axial point. Hope this is clear to you. Now let us calculate the electric field intensity on the equatorial point for this electric dipole. So this is the electric dipole, minus q plus q charges. Now my point of observation or calculation is on the equatorial line. So that is a perpendicular bisector to this dipole. For that, I need to draw this distance from minus q and plus q. So due to plus q, the electric field intensity at point P, again at point P, there we consider a unit positive test charge, that is a positive test charge, so the electric field intensity will be away from the point P. Here is the minus q charge, the electric field intensity will be towards minus q charge. So this side of this triangle is A, and this side for this triangle is A, and this is the center of dipole O. This is r distance, this point P is r distance point from the center of the dipole. So I want to know the electric field intensity at point P, that is on the equatorial line. I want to know the electric field intensity at this point. So I know this distance is A. I have this distance as r. That is r distance from the point P. So from this right triangle, if this angle is theta, and this angle is also theta, then this angle will be 2 theta, because this is an exterior angle, or to this triangle. For this triangle, this is an exterior triangle, so the exterior triangle is always equal to the sum of the two interior opposite angles. So also from this right triangle, I can write this distance is r square plus a square. Similarly, this distance is r square plus a square. So I can write the electric field intensity due to the plus q charge as E plus q equal to q over 4 pi epsilon naught divided by the distance square, that is r square plus a square. This gives me the electric field intensity due to the plus q charge. Similarly, the electric field intensity due to minus q charge will be again q over 4 pi epsilon naught r square plus a square. This E plus q I call, suppose for E1, I call this as E2. So this is my E1 vector pointing away from point P, and this is my E2 vector away from point towards the minus q charge. So since the magnitude of the two vectors, two electric field is same, so I can write this as equal to E, and this is equal to E. The resultant of these two electric fields are, I can write it as E square plus E square, that is E1 square plus E2 square plus 2 E1 E2 cos of the angle between the two vectors, that is 2 theta. This will give me the resultant of these two electric fields. So the R will be equal to E square plus E square, 2E square will I take common, and I am left with 1 plus cos of 2 theta. The R, resultant of the two vectors, resultant of the two electric fields will be under root of 2 E square, using the identity 1 plus cos 2 theta equal to 2i cos square theta. So R will be equal to 2 E cos of theta. This will be the resultant of these two electric fields. Due to the plus q charge, due to the minus q charge, the resultant will be along the diagonal of this parallelogram. To complete this parallelogram, it will be along this direction, and the magnitude is equal to 2 times E cos theta. So I can use this triangle to calculate the value of cos theta in terms of R and A. So cos theta is base over hypotenuse. I can write cos theta equal to base is A and the hypotenuse is under root of R square plus A square. So I can substitute in this expression E net, which is the resultant electric field, E net on the equatorial line, 2 times E. E is one of the two values here, E1 or E2. So it is q over 4 pi epsilon naught r square plus a square, and cos theta is a over under root of r square plus a square, so it will be 3 over 2. I already have defined the electrodipole moment for this electrodipole, that is P is equal to 2a into q. This gives me the electrodipole moment. So E net on the equatorial line will be P over 4 pi epsilon naught r square plus a square 3 by 2. This gives me the net electric field intensity in terms of the dipole moment. If I take the direction or the vector, what will be this E net equatorial, that is in vector form, it will be minus p over 4 pi epsilon naught r square plus a square 3 over 2. Why minus p? Because the net electric field intensity is having a opposite direction to that of the p. P is directed from minus q to plus q conventionally, but the electric field intensity here comes out to be in the opposite direction, that is from plus q to minus q. So this minus q minus sign here takes the care of direction. Now let us see the special case, what will be the electric field intensity when the dipole is very short, or this point of P is far away from the center of the dipole. In that case, again r square plus a square will be equal to a r square. So E net equatorial will be minus p over 4 pi epsilon naught. I will write in place of r square plus a square, I will write as r square. So it will be r square to the power 3 over 2. So this square and root gets cancelled, so we are left with r cube. So this is the expression for the equatorial electric field, and this is the expression for the axial electric field due to the dipole. We can easily see that this axial electric field, the axial at axial point, let's only take the magnitude. At axial point, same distance r, on the equatorial line it is 2 times equatorial in terms of the magnitude, and in terms of the direction they are opposite. In that case, axial line, the electric field intensity is along the direction of the dipole moment, but in equatorial case the electric field is opposite to the dipole moment. Thank you.